Santiago. I'm an engineer at Aztec Labs. And well, today's talk will be split into three. We'll start with a very high-level discussion, then we'll go very, very low level into technical details, and then something in between. So hopefully there'll be content for everyone, and also no one that will enjoy the whole talk. Let's start on privacy and censorship resistance and the link between the two, also known as how I convinced Tim and Tina to get me on stage today. So, first of all, why privacy? We have said a million times that privacy is a human right, and it's not just that, it's that the whole world around us is private. Like, our users expect privacy from every application they use, where it's finance, it's banking, it's voting, gaming. It's not that if I don't need privacy if I got nothing to hide. It's that everything is and should be private by default. But the actual question is not why privacy, but why privacy at this event, right? And the catch is that privacy is one of the means, one of many, to guarantee censorship resistance. If I cannot discriminate something, I cannot censor it. In particular, I really liked a quote by Jordi during a panel a couple of days ago when discussing the privacy aspect of zero-knowledge proofs, that CKPs are not a means of hiding, but of revealing exactly what is meant to be revealed and nothing else. Like that goes back to a typical example, right? If I'm opening a bank account, I shouldn't be revealing my age, my race, my gender, where I live, etc. Should be just revealing the exact information needed. And like, I really like the analogy, because with smart contracts we are used at having code that is low when it comes to execution, and with zero-knowledge proofs and privacy, we're defining the rules of what exactly gets revealed for each application. And we can all agree on that. And we cannot have a third party pop up and suddenly start censoring based on information that they shouldn't have had access to in the first place. And the thing is that we have already been using privacy in the context of Ethereum already for some time, or at least have been discussing about it. I see that I'm the second person in a row to have a reference to John in their slides. But for instance, encrypted mempools is a way of using privacy to prevent not just toxic MEV extraction, but also to prevent censorship. A sequencer that cannot see inside the transaction cannot censor it. So, hopefully, I've convinced you that privacy makes sense in the context of censorship, so I can now go into what I wanted to discuss in the first place, which is how we implement this. So, what is privacy for us in the context of the Aztec network? Just the only shield, and for setting context, Aztec network is a private first L2 that works on Ethereum. That's fully programmable. That's all you need to know. So we're seeing it as a private user identity, private function execution, operating on private state. So for any third-party observer of a transaction that happens on the network, it should be that someone has done something on some state, on some function, some contract. Basically, nothing gets revealed. We want to make sure that there is zero information leaked whenever a transaction is sent, while retaining full programmability. So how do we do that? We do that by moving execution from the sequencer, from the nodes, to the client. So whenever a user sends a transaction in the network, what we do is we execute that transaction locally and generate a zero-knowledge proof of validity for that transaction. So what that means is that every transaction that's sitting on the pool, on the mempool, is a zero-knowledge proof that proves the validity of that execution with a set of state changes that are completely opaque to a third-party observer. And that's it. There is no information leaked whatsoever. How do we do that? Basically, for every function in every contract on the network, we generate a unique circuit. So when we're writing a contract in this context, each of these functions will be compiled to a unique circuit. And we choose to do it that way and not by virtue of a VM, because these functions need to be proven client-side. We want each of these proofs to be generated in a browser with 1 gigabyte of RAM in a mobile device. We cannot ask for half a terabyte of RAM in order to generate a proof for a user. Not given that we want the user to keep privacy by running everything locally. So how does it look like? Basically, each function, each call within the stack generates a zero-knowledge proof of correct execution, and that gets aggregated recursively with another circuit, which we call the kernel circuit, taking terminology from SIGSI. And that circuit takes care of basically gluing together the entire call stack, hiding any sort of information. The kernel circuit also is going to hide exactly which function and which contract got executed, and produce a single zero-knowledge proof for the entire transaction. So this means that each of these individual proofs is small enough to be run in consumer-grade hardware, in a mobile phone, and then gets aggregated and broadcasted to the network. But if we're running private execution client-side on each user, we need a representation of state that's amenable to this kind of execution, right? Like in the EVM, we have account-based state that works wonderfully because we can have multiple transactions all operating simultaneously on the same state. Here, if different users are working together, it's a bit more difficult to map that to account-based storage. Not just that, we will also end up leaking information if we have subsequent updates to the same storage slot. So for private execution, we use a different representation of state. We take a page out of Zcash, out of Bitcoin, and use a UTXO-like model in which we have custom nodes representing state. And I want to highlight here custom, like every smart contract, every dev can define the shape of the nodes for representing their own state. Like for a payments application or for a token, let's say, a value node that just carries the value, the amount of funds in that particular node is enough, which is the shape that we're already used to. But let's say that we're building something like a card game, like a Magic the Gathering inspired one, in which we can represent, for instance, each card with a specific node that has the attributes of that particular card. Again, the nodes are the representation of state and are not bound to financial applications. They are completely custom and used to represent arbitrary state. Now, these nodes are stored locally by each user. So each user has their own representation, their own private state, which is kept locally within their wallet. But we need to map those nodes, that private state, to the global blockchain state, right? This means that whenever I want to send information to another user, I create a node for that, I encrypt it with a recipient's public key and broadcast it through a network so to make sure and to provably send it to them. But I also need to create a commitment to that node in what we call a global data commitments tree. In other words, if the only proof I have for using a node is that I have it locally, users could be able to create nodes, create state out of thin air. So whenever a node is created, we add a commitment, a hidden commitment to it in what we call a private data tree. So whenever a user needs to generate a proof that uses this particular piece of state, they need to prove membership of that node in this Merkle tree. Consuming a node, basically deleting a node, render it outdated, is done by nullifying the node. Node is nullified by emitting what we call a nullifier, which is a hash of the node mixed with a secret generated by the user in a deterministic way, such that the nullifier cannot be linked to the node commitment. In other words, when we create a node, we add it to an append-only tree. When we want to consume a node, we just register that it was used without any observable link back to the node. This allows us to update nodes, to change state, without having any link between the transactions. How does this look in code? We are using Noir, which is a Rust-like DSL for writing circuits, augmented with a framework for writing contracts and having easy interaction with private state. Here in particular, we have an implementation of a very simple counter contract that keeps a counter for different users and allows incrementing them. And what's interesting is how this is implemented with nodes under the hood. So what ends up happening is that we have one node representing state, in this case, one node for each counter of each user, and when we want to update it, we consume the node with the old value, again by emitting a nullifier, and create the new one. So basically updating state is deleting the node that represents the old state and creating a new one. And by virtue of nullifiers, there is no link between the two operations. So we're effectively updating the same slot without revealing any linkage between the two. It's also worth mentioning that whenever a user needs to read a value of a node, needs to create a proof by using a value of a node, we need to destroy the node and recreate it with the same value. Why? Because if execution happens in the user device, it needs to happen on an old version of state. Like the user doesn't know when their transaction will land in a block. They don't know what's the exact state that their transaction is going to operate in. That means that the only way to ensure that they have a fresh version of state is by consuming it and generating it again. If they happen to be using an old version of state, they would be emitting a nullifier associated to that piece of state. It will already be in the tree, and it will be registered as a double spend, which is the only other condition we have for validity for transactions. Transactions are zero knowledge proof and are valid as long as that proof is valid and there are no duplicate nullifiers. So bottom line here is we have a state representation that allows us for each user to run functions privately, generate a proof of them, and broadcast those changes in an opaque way. However, it's worth mentioning that if every time we need to read a value, we need to invalidate it and recreate it, which implicitly invalidates all other transactions in the pool that we're referring to it, this doesn't align well with composition, right? Like it's known that CK snarks are maybe not the best tool when it comes to concurrent updates to the same shared private state. So for instance, this model is great for implementing a private order-based DEX, but not so good when we want to do an AMM, where we have a single shared, constantly updated piece of data, such as the liquidity, the amount of each token in the pool, that gets constantly updated. So to address that, the network actually runs a hybrid model, private and public. What does it mean? This means that every transaction, along with a set of opaque state changes, can also emit a set of execution requests. And here we are in the land that we're familiar with. Basically, the transaction asks the sequencer to run a series of public executions on their behalf. And here, public functions map to an account-based state, similar to the one from the EVM, and can concurrently operate on the same state. However, having this duplicity of both private and public state in the same chain makes it easy to run operations such as gathering and unlocking funds based on some sort of private condition, then swapping them in public state, and then shielding them back into private state. The idea is that every private transaction can enqueue a set of requests to be executed in public. But how the developer manages this difference allows for this duplicity of, okay, what needs to be run in private, what needs to be run in public. What's the problem here? Even though we have made composability easier, now we're introducing a censorship vector. We're starting to reveal actions that transactions do. And with that, let's go into the third and last part of the talk, which is about decentralization. Given that we're building a network, private first, in which censorship is of the utmost importance, we want to make sure that transactions cannot be censored, cannot be stopped. And for that, we're designing sequencing and proving protocols that are both fully decentralized, that are going to be decentralized from day one. The network is not going to launch without fully decentralized sequencers and provers. Progressive decentralization is not an option here. And we're also working on governance mechanisms that are compatible with them, that can provide security, provide upgrade paths, but guaranteeing the censorship resistance of their users. And we are doing this decentralization in a decentralized way. We are putting out, and we have been putting out RFPs throughout the year, asking the community to contribute with proposals for each of these areas. And we'll continue doing this. And we really, really encourage you to jump into the forum, link in a couple slides, and help us here. We're converging to a sequencer selection algorithm called Fernet. Apparently an Argentinian guy named it, which basically depends on random elections of stake sequencers on the network based on a verifiable random function. The idea behind this is having promoting decentralization among the set of sequencers. And we're currently evaluating different options for proving that pair well with the sequencer proposal, both cooperative and competitive networks. In competitive networks, we know that we can foster innovation, competition between the different providers in researching better techniques for faster and cheaper proving. And in cooperative networks, we know that we can foster a higher diversity, which should lead to lower censorship. In particular, in Aztec, we have designed a rollup topology that, if we want to, allows us to parallelize the proving across many, many different machines that can run in consumer-grade hardware. Like each of these small nodes within the massive proof tree should take no more than around 32 gigabytes of RAM, give or take. So again, we can completely parallelize and decentralize the proving activities. So, to sum up, we have a lot of problems to figure out, a lot of challenges ahead, and I encourage you to please join the forum, join the discussion, help us build strong, robust, healthy, private and censorship resistance protocols, not just for the network that we're building, but also to generate open source knowledge that can ideally help all other networks in the Ethereum ecosystem. Thanks.